This is a PowerPoint on how to determine the molecular geometry of a molecule. And you should watch part 1 first, and that will help you know what the geometries are. This will do examples how to actually come up with molecular geometry for molecules. First thing to do is to write a valid Lewis structure. And if there are resonance structures, just pick one. It doesn't really matter which one you pick. Step 2 is to count the electron domains around the central atom. And this will give you the electron domain geometry. There are 5 possibilities. Next, count the lone pairs and the bond domains, and that will give you the molecular geometry. So you use the table to determine what the molecular geometry is. And remember, you need to memorize these because on exams you need to know the geometries. You won't have the table. Now, one of the things you have to know is how to read a 3D sketch of a molecule. So if you look here, you'll notice that the lines are in the plane. So this is ammonia, and this line here is in the plane. A wedge, a dark wedge, comes out of the plane toward you, and you can compare that to the molecule at the bottom, the picture. And the dotted wedges or lines go back into the plane. So the dotted lines go back. Again, you can look at the picture of the molecule on the bottom. We're going to use those kinds of sketches to show what the geometry of the molecules actually look like. Example 1, carbon tetrachloride. The first thing to do is to write the Lewis structure. To write the Lewis structure, you need to count the valence electrons. There are 32, and this is what it looks like. Notice that everything has an octet, and there are no resonance structures here. Next step is to count the electron domains around the carbon. You're counting the electron domains around the central atom. There are 4. They are all bond domains, no lone pairs. From that, you can look on the table and find that the electron domain geometry is tetrahedral. If there are 4 electron domains, the geometry is tetrahedral. The bond angle is 109.5. Since all of the electron domains are bond domains, then the molecular geometry is also tetrahedral, and the bond angles are 109.5. At the bottom you can see the picture of the molecule with the wedge showing the bottom chlorine coming out at you and the one on the left going back into the plane. Example 2, ammonia. Again, write the Lewis structure. It has 8 valence electrons, so that is the Lewis structure. Next, we count the electron domains around the nitrogen, which is the central atom. There are 4 electron domains, 3 bonds, and 1 lone pair. Therefore, the electron domain geometry is tetrahedral. If there are 4 electron domains, the electron domain geometry is tetrahedral. The molecular geometry only counts atoms. It doesn't count lone pairs. The molecular geometry with 3 bond domains and 1 lone pair is trigonal pyramidal. Bond angles are somewhat less than 109.5. Remember, it's distorted because the lone pairs take up more space and they push the other atoms closer together. And at the bottom there you can see the sketch of the geometry. Example 3 is ozone. So we write the Lewis structure. It has 18 valence electrons, and this is what it looks like. Now, there are resonance structures here, but they don't affect the geometry because multiple bonds count as 1 bond domain. So it doesn't matter which one we pick, and we'll just do the one at the top there. Alright, counting electron domains around the central atom, the central oxygen. There are 3 of them. 2 are bonds, and 1 is a lone pair. Notice that the double bond counts as 1 bond domain, 1 electron domain. The electron domain geometry is trigonal planar. The molecular geometry, counting only the atoms, is bent. And the bond angles are less than 120 degrees. It's distorted because the lone pair is taking up more space. Example 4, carbon dioxide. We write the Lewis structure. It has 16 valence electrons. There are 2 double bonds around the carbon, which means there are 2 bond domains and no lone pairs. The electron domain geometry is linear, as well as the molecular geometry, and the bond angles are 180 degrees. Example 5 is this molecule here, has 24 valence electrons, and there's the Lewis structure. We count the electron domains around the central carbon. There are 3 of them. 2 single bonds and 1 double bond gives us 3 bond domains. There are no lone pairs. So the electron domain geometry is trigonal planar, and the molecular geometry is also trigonal planar. The bond angles are distorted. The ones between the oxygen and the chlorine are slightly larger than 120, and the chlorine-carbon-chlorine bond angle is slightly less than 120 degrees. Example 6, sulfur tetrafluoride. We write the Lewis structure as 42 valence electrons, so this has an expanded octet, more than an octet. We count the electron domains around the sulfur. There are 5, 4 bond domains, and 1 lone pair. Notice that if we hadn't done the Lewis structure here, we would expect it to be tetrahedral. SF4 looks like there would be 4 bond domains around the sulfur. So you need to count the valence electrons and do a proper Lewis structure, which shows that this is an expanded octet. The electron domain geometry is trigonal bipyramidal with 5 electron domains. The molecular geometry is seesaw, and the bond angles are distorted again, slightly less than 90 and less than 120 degrees because of that lone pair. Example 7, iodine pentafluoride. We have 44 valence electrons. We write the Lewis structure and it looks like this. Counting electron domains around the iodine, there are 6, 5 bond domains, and 1 lone pair. So the electron domain geometry is octahedral, the molecular geometry is square pyramidal, and the bond angles are slightly less than 90 degrees. VSEPR also works with larger molecules, and what we do with it is we predict the geometry around each individual atom. So if we look at this molecule here, the black ones are carbons, the white ones are hydrogen, and the red is oxygen. So if we look at the first carbon on the left, the electron domain geometry is tetrahedral because there are 4 electron domains, and the molecular geometry is also tetrahedral. For the carbon in the middle, the electron domain geometry is trigonal planar, and the molecular geometry is also trigonal planar. There are no electron pairs around that carbon. There are just 3 bond domains. Around the oxygen on the right, the electron domain geometry is tetrahedral, the molecular geometry is bent. Now how do we know that? The only way we can know that is to actually do the Lewis structure and show the lone pairs, the 2 lone pairs around the oxygen. And if you look at that molecule, you know there has to be lone pairs around the oxygen, otherwise the geometry would be linear. Since it's obviously not linear, there have to be lone pairs around that oxygen.